All right, so right now, all of you should be seeing, it says Chapter 5, T5, Electrical Principles.
Got it.
All right, and I will ask all of you, it's not a huge group, so with 8 of you, if you have a question, ask the question. Because if you have a question, guarantee somebody else in the group has the same question. And so don't hesitate to interrupt. Most of this is when we get to the questions, we're going to go through the material with you, some of these things I've shared to you, but ask, it's better to understand it right away. And these are really foundationals. Electrical principles are really principles. You're going to use these when you get into your tech, your general, your extra, all the way through. A lot of this applies to even things in your own home right now. So what we're covering today is T5, electrical principles. It's broken into several pieces. The first one is looking at, talks about basic things, current and voltage, math for electrical, electronics, reactive elements, and Ohm's law. Reactive elements we'll touch on later because you're going, what on earth is it? But if you look on the right, and I'm scrolling down, is it all large enough for people to see? I do want to ask that. Probably James with an iPhone is the poorest image, but
That's fine.
good. All right, electrical quantities, it shows in both tables. There's current, and that's the flow of electrons. And current means if you, for example, if you're on a river, how many gallons a minute go by? It's not how hard it goes by. It could be falling on a waterfall and crushing you to death. And if it was the same total volume, that's current. It's how much electricity goes through the volume of it. Voltage is how hard it pushes. So if you're on a gentle flowing river, there's not much force pushing the water through. The steeper it is, the more push it has. That's voltage. Voltage is how hard you push. So, and you can easily think of that. You've all used pressure washers. When you just use a hose, it doesn't blast stuff around. The pressure washes, raises the pressure, that's the voltage, to push it faster. And the combination of current and voltage is the power. A hose doesn't have much power, the pressure washer does, even if they're giving the same amount of water. So the same current. Then resistance is the opposition to the flow of the current. And there are two kinds of resistance we normally think of, and we'll get to it more, but it's like trying to shove water through a tiny little hose or a big hose. If you're going to take a long run for a hose in the garden, the large diameter ones flow well. Little ones, it resists the flow, and it's nothing, it's the opposition to flow of electricity. There's a special version we'll touch on called impedance, and that is the resistance to alternating current. And then capacitance. Capacitance is you store power, yeah, I'm going to say power, energy in an electric field. And the classic symbol is a straight line, a little curved piece. It's imagining storing it between the spaces. There's no magnets involved. It's a electric field. Static electricity is stored capacitively on our bodies. When you shuffle your feet, purchased a big capacitor, and that arc that goes off, that's capacitive charge that was stored in us. Inductance is where you store it in a magnetic field. And that's the things you, well, if you're old enough, the coil in your car that gives high voltage stores it in a magnetic field, releases it suddenly and comes out really high. And then powers the total thing. When you turn on, you can have a dim light bulb that's 1 watt, or a bright one that's 100 or 5,000 watts. That's what we pay for. When we buy our electricity, it's a combination of the voltage and the current. The two multiplied together, that's power. The more you use, the more we pay. We're fortunate here. Here in Washington, a lot of you are in California. You may probably pay more than we do. So those are the initial things to cover there. The concept: current and voltage, resistance, capacitance, inductance. Those are reactive, and power. I'm going to scroll down. We're going to go to Ohm's law. It's not the one I want. Ohm's law is something we're going to cover. This is the overview before we get to the questions. Ohm's law is the relation between V, which is voltage, and often represented by the letter E. So when you see E, you think voltage. I is current, and R is the resistance. And it's the whole relationship for the voltage, current, and the resistance. This little drawing I gave you is the important part. When we go to calculate it, let me scroll on. Where's the right one? Oh, I got to move my picture away. There we go. And that little triangle here, it's represented by a circle, but it's still the E at the top, the I, and the R. And to find voltage, you would say, I want the E, so cover that with your thumb. You multiply current times resistance. To find current, which is the I, you'd say E divided by R. The voltage divided by resistance. Resistance is voltage divided by current. So that little triangle that we showed first is a really simple way to handle this, and you use this as a tool. This triangle back here, this is what I tell you when you're going to take your test. That's one thing you might draw, triangle or circle, it doesn't matter, but that pattern, and that will really help you. Instead of remembering multiply like it's shown here where voltage form, instead of remembering these equations, they're short, think of this and you have the whole relationship. Parallel and serial circuits. If you look at the top, here's a source, we'll call this the battery or the electricity, and it's flowing in a circle going through one whatever, through another whatever. It's in series. It goes straight through all of them. Here, the two widgets are next to each other. The power goes to both, goes through both independently. They are in parallel. It's like this is a one-lane road with two trucks on it. This is the freeway. You got two lanes. They can run parallel. That's the difference. They can go different speeds, have different use. Unit conversions. Let me bring that up. Unit conversions can be styming. Most of you probably know the word kilo because we hear a kilobuck. It's $1,000. And we hear, if you use the metric system, you may use familiar with centimeter, meter, and centimeter. Centa means 100, so it's smaller than one. Here's one, like 1 meter. A centimeter's that short little bit. There are others we don't use, like decimeter, millimeter we do. That's, you notice, a tenth of what a centimeter is. The ones in here we use pretty regularly are kilo, and it's this K for like kilohertz frequencies, kilowatts, kilovolts. And you also see mega. The big M is for a million. Those are the kilobuck, kilo, and a mega are 1,000 apart. In fact, you see this whole series goes 1,000 at a step, except right at the beginning. We don't tend not to use the 10 or this. We get to 100 and then we're going kilo, mega, it's 1,000 times. Three zeros get added. Getting smaller, here's the primary one. We often use one, and electrically we use millivolts and milliwatts. That's kind of the next step. So it's 1,000ths of the one. And then micro is another 1,000 smaller. It's a millionth. And you can see these other tiny ones that are much smaller. You don't see them very often. They're in the test, but it's not a dominant thing. But understanding this conversion factor going from, 1 to 1,000 to a million, and going the other way, going from 1 to a milli, 1,000ths, is really, really important. Decibels, I didn't grab let me see if I can get the slide. Decibels is a unit that we hear in sound. We also use it electrically. And one way to remember this calculation here, it looks confusing. Most of you don't care. If anybody's an engineer, you may know these things. You know what 10 log 10 is. But the important thing is, here we go. this first table is addressing, pull it down, addressing common decibel values, and it is decibel, a tenth. So the important one to remember, if you have 3 decibel gain, you've doubled whatever it is. If it's for sound or watts, 3 decibels is doubling it. So if you double it again to 6 decibels, now it's 2 times that, now it's 4. And then you notice they say 10 decibels is 10, factor of 10, 20 is 100, 30 is 1,000. So you see it increases rapidly. But for you to remember, 3 decibels doubles it. That covers a lot of what you really need to know. Make sense? Bueller? Okay. I love to, I really enjoy teaching when you can see the people more. So the questions in here are electrical currents measured what units? You want to unmute and you can actually interact with me. I know we're there. As long as you don't have background. Well, electric current, you measure it in amperes, amps. And most of us will just say, how many amps is it? It's amperes. That's the unit of current, the volume. It's the gallons, if you like. And electrical power, the next question, you measure it in watts. That's what we pay. We pay for electricity for our homes by kilowatt, by 1,000 watts. For an hour is the equivalent. But watts is how much power. That's when you look at your hair dryer, it's often 1,200 watts. You can run one of those in a circuit. 2 of them, you'll pop the circuit. It's too much power. So electrically is in powers in watts. The name for the flow of electrons is current. And you measure that by amperes. Watts here is the power one. Let me scroll down. Electrical resistance is in ohms. And remember, we had Ohm's law that had this nice little circle. If you remember, the R is resistance and it's Ohm's law is what it is, term for what causes electron flow. And that is going to be voltage. Remember, we talked about how hard you push. That's the force that pushes the current through. And EMF is electromagnetic force. There's a lot of abbreviations we use. Again, if you have a question, ask. Unit of frequency. I'm looking at Mark. Mark remembers when we put, and maybe the other folks down there at Fort Bragg, we grew up with CPS, cycles per second. Well, Hertz is a famous early scientist involved in electricity, and we renamed cycles per second Hertz. So Hertz fundamentally means cycles per second is how many waves go by. When you look at the beach and you hear a wave going splash, 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 or you could say it's 1 wave per second. The frequency is 1 per second. You go out to the ocean where it comes in every 30 seconds, it's, only 1 per 30 seconds. That's frequency. So Hertz is what we used. These other ones, Henry and Farad, are for capacitance and inductance. Tesla is a magnetic field, like on the Earth. They ask, what metals are generally good conductors of electricity? Why are they? And you look at these, they have a high density. Well, aluminum is lower density than others, and it works. Protons, a lot of free electrons. Electricity, we think, is the flow of electrons. If they're free to move, you can push them around with electromotive force and have current. And somewhere you read that glass is not a good conductor. Oddly enough, once you get it where it's slumping, it actually lets current flow through high resistance. Industrial furnaces put electrodes in and cook it like you would a hot dog and 2 nails, because it resists the flow. But when it's, what we think was solid, it's not a conductor. Which is a good electrical insulator? Glass. We just addressed all the metals. Alternating current, what is it? And I already described alternating current. In our homes, we use AC, alternating current. Edison wanted DC, direct current. And alternating current literally the electrons are going one way, then they go back the other, back and forth. And where we live, this full cycle from one to the other and back happens 60 times a second. In fact, when you get into radio, you realize you recognize 60 hertz because that's often noise that gets in from our wall warts and transformers and power supplies. So we often hear a buzz at 60 cycles, and that's part of that alternating current. And big advantage is it's easy to change it through a transformer to other voltages. DC's a little harder to do. That's one reason Westinghouse went and pushed AC. DC, oddly enough, for the folks in Fort Bragg, here up on the Columbia River, our dams make some power, and some of it gets turned into 1,000,000 volt DC. Big power line goes through Eastern Oregon down, I think, clear to LA. It carries it more efficiently than AC over long distance. So, and then they got to convert it back because AC is what we want in our house, the transformers and the pole that give us our power. Which term rate, what rate describes the rate electricity is used? And that's again power, the watts. We pay by the 1,000 watt hour. 1,000 watts for an hour is what our fundamental unit is. What type of current's opposed by flow is opposed drive resistance? And I mentioned direct current, it wants to go, but it'll light up a light bulb, that's high resistance. AC is resistant. And RF current is resistant as well. So all of these are correct. All of those have resistance that we experience that sees. What describes the number of times per second an alternating current makes a complete cycle? I think we just talked about it. It's frequency. And just so you think about it, wavelength is talked about when we get to radio. I mentioned going to the beach, little waves going splash, splash. They're only a foot apart. We go to the ocean where there's swell and we have one wave every 30 seconds. They're hundreds of yards apart. That's wavelength. And we talk about radio both by frequency, also fairly often by wavelength. Math. Remember the table, this one I have up. This is all about these factors of 10 and 1,000. How many milliamperes in 1.5 ampere? Well, we said a milliamp is 1,000th of an amp. So to go from 1.5 and multiply by 1,000, we have 1,500 milliamps. And I'm abbreviating it milliamps. Again, milliamperes is the full term. Rarely said. Milliamps is the classic way people will say it. Then they have the question, what's equal to 1.5 million hertz? Well, hertz, and I said million. Well, it's not 1,500 million hertz. What would it be here? Well, the only thing that matches, this is too big a number. That's already a million. Gigahertz is 1,000 more. Kilohertz, it's not enough. But 1,500 kilohertz is lopping off the last three zeros. They're your kilohertz. And we do a lot in megahertz and kilohertz both. So make sure you understand the difference. Megahertz and kilohertz, they're 1,000 apart using the table over here. What's 1 kilovolt? We pretty much touched it. 1,000 volts. Kilo is 1,000. 1 kilovolt. What's equal to 1 microvolt? And if we look over here, we see micro is 1 after 3 zeros, so it's 1/1,000,000th of a volt. And there's your A, 1/1,000,000th of a volt. So micro is a millionth. Milli is 1,000th. Those two are the ones you see probably the most. There is a question about pico, and I think there's just one in here. So the next question, what's equal to 500 milliwatts? And a milliwatt, 1,000 milliwatts is 1 because is 1 watt. So 500 milliwatts is half a watt. And we use these numbers very often talking about little devices like, here's a radio device that I can talk to on my handheld and it will talk back. And it only puts out about 1/10 of a watt, so about 100 milliwatts. A lot of Small unlicensed radios put out up to 100 milliwatts. Our handhelds that you will end up getting too many of in the end, like most of us. Most of these put out 5 watts total. So there are differences in power depending on your need. My big amplifier down here can put out 1,500 watts. Most of our high frequency radios put out 100 or less, but understanding the difference between milliwatts, watts, kilowatts is very important. The next one is what's equal to 3,000 milliamperes? Bueller, we said it's milli, so this is 3,000, so it must be 3 amperes, because this is 1,000, knock off the 1,000, there you got the 3. What's equal to 3.525 megahertz? You've got to learn what the meanings is. There's the million, hertz is starts with a capital, and 3.5 megahertz. Well, we could, if we just added zeros, we could have kilohertz, which there it is. I didn't even look at the answer. We just thought, what are they likely to do? So 3,525 kilohertz is 3.5 megahertz. Remember, kilohertz is 1,000th of a megahertz. What's equivalent to a 1 million picofarads? Here's the trick one. And if we look over here, picofarads has 1, 2, 3, 4. It's way out here. And from pico to micro is a million. So we can lop off 2 of these. It's going to be 1 microfarad. And here's this micro, the little U backwards looking Y or U is a microfarad. So this is the one question you may just want to remember, because most of us don't remember the nano, pico, femto, alt, atto. They're units that if you're a scientist, you may use these regularly, but most of us only use those initial fews I described. What decibel value describes which one most closely represents a power increase from 5 watts to 10 watts? Well, from 5 to 10 is double. It's doubling. And I said the one thing to remember is, 3 decibel is a doubling of whatever you're measuring in decibels. So the answer is going to be 3 decibels. And that's what they come. It's and if we, in this last one be going, it's a factor of 10, that would have been from 5 to 50. But remembering that doubling is the easy way to do it. Which decibel value most closely represents a power decrease from 12 to 3 watts? Well, I can say 12, I cut it in half, that's 6, cut it in half again, that's 3 watts. Well, every halving is 3 decibels. So I come up with minus 6 decibels, which is the answer that's correct. And what's the next one? What's equal to, oh, here's the one. A decibel changes from 20 watts to 200. Did I skip a page? No. From 20 watts to, I hate how it jumps. Roll to 3. Which decimal value represents a power increase from 20 watts to 200? As I said, that's a factor of 10, and that's 10 decibels. So that one's easy to do. The doubling is where you are more likely to remember. What's equal to 28,400 kilohertz? Well, again, let's lop off this, because the would be 28.4 megahertz, and there's the answer right here in front of us. These things tend to be going from kilo to megahertz. I'm sorry, that's kilohertz. 28.4 megahertz. So think of things in unit changes of 1,000 between kilo and mega. What's equal to 2,425 megahertz? This one, if we look, the choices are going to be, they only give you gigahertz, and gigahertz over here is 1,000 more than a kilohertz. than a megahertz. So we can say this is going to be 2.4 gigahertz, 2.425. So again, simple math. Think of this table. Remember, most of the steps are in units of 1,000. So reactive elements, capacitance, inductance, radio frequency definition units, we've kind of looked at in calculating power. Let me go to here. What describes the ability to store energy in an electric field? And remember, the choices are, we're really looking at chemicals like a battery. When we say electric field versus a magnetic field, an electric field stores it as its capacitance. So if you just remember capacitance, the symbology when you get to diagrams, capacitors look like two plates, two lines, a curved line and a straight line. And what's the unit of capacitance? Capacitance is farads. I don't know how to any neat way to make you remember farads, but farad is capacitance, and in this text below it, it talks about inductance as the Henry. And the next question is, what describes the ability to store energy in a magnetic field? And that is inductance. It's if you have a coil of wire and you put current through it, it will create a magnetic field. There is energy stored there. When you let the power off, the magnetic field collapses and comes back as our electrical energy. And that is inductance. In fact, a lot of you may have, the world seems to be trying to get rid of our natural gas, and they have stoves now that you just put the metal pot on and they get hot, but nothing gets hot except the pot. That's an inductive reaction. A magnetic field causes the metal to get hot. It's heating it up. It's not quite like microwave, but close enough. What's the unit of inductance? We already said that's the Henry. I don't know how to remember it. Farad is capacitance, Henry's inductance. What's the unit of impedance? Well, that could be somebody pushing at your front doors to impede them from entering. It's a unit of resistance, and that is ohms. All you got to remember is ohm is a resistive thing. It's the unit for resistance. What's abbreviation for RF? A lot of us use it. RF just stands for radio frequency, and we'll talk about radio frequency energy, what gets emitted. The microwave use radio frequency energy to cook our food. So they're looking for a answer, radio frequency signals of all types. And it's around us all the time. And your ability now is you're going to be a ham to detect it. You think our little 5-watt radio puts out this much energy, yet our handheld can detect it several miles away. I can talk in 5 watts and talk to somebody in the Bay Area on certain frequencies. So our systems detect minuscule amount. It's around us all the time. Abbreviation for megahertz, we covered it. It's capital M in the hertz, megahertz. And formula to calculate power in a DC circuit, well, here is, I mentioned, I showed you, this was the look like Ohm's law, but this is the power formula. So if you have power, you want to know that, you multiply current times voltage. And that's what's described here. So we find where E times I, power equals E times I, so it's A. And this is another thing to draw as well as Ohm's law when you take a test. It'll keep it running for you. And I'll show you one more. I don't know if I showed this. For Ohm's law, we'll get to it. I did show it to you. How much power is delivered by a voltage of 13.8 volts DC and a current of 10 amps? Well, remember, power, go back to the power one. Power is current times voltage. So we have those two. We have 13.8 times 10. That's 138 watts. This is a really useful tool. How much power is delivered by a voltage of 12 volts DC and a current of 2.5? This could be the same thing. Power is current times voltage, 2.5 times 12, 30 watts. And even if you don't do the math, you can go, these other numbers are a bit wonky. So it's 30. I love multiple choice. How much current is required to deliver 120 watts at a voltage of 12 volts? This is where, again, draw the picture. They're asking what is the current. So the current we want is the power over the voltage. So 120 divided by 12, it's going to be 10 amps. Make these drawings when you take your test. It's quick to, instead of thinking these formulas, get it off of these things. What is impedance? An impedance is a particular kind of resistance. It's the opposition to alternating current flow. And the next one is, what's the abbreviation for kilohertz? And let me scroll down. The K. So the little K, lost where it went. It's going to be little K and then big. So here's kilohertz. And if we go back, we had, it's described in another spot. Ohm's law. I'm going to go back to Ohm's law. In fact, I'll put this one up. What formula is used to calculate current? Well, again, I come back here. Current is this one. So it's E, voltage, over resistance. We find I is E over resistance, B. And this is the way to make it really easy. Instead of memorizing multiple formulas, just keep this in mind. What formula is used? We did that one. What formula is used to calculate voltage in the circuit? Well, voltage is E, so we want to calculate I times R, current times resistant. I times R, so that's going to be answer A again. What formula is used to calculate resistance? Well, I'll go over resistance. You find E over I, voltage over divided by current. Doing these little simple tools really makes the whole testing thing a lot easier for you. One more, here we go. What is the resistance in a circuit with a current of 3 amps flowing when connected to 90 volts? Well, again, they're asking the resistance is E over I. So there's 90 volts over 3 amps. So it's going to be 30 ohms. I really can't but stress how practical it is. What's the resistance when applied voltage is 12 volts and the current is 1.5 amps? Well, again, resistance we want to find. So we're going to go E over I, voltage over amps, 12 over 1.5. Well, even without doing the math, it's going to be 8 ohms. Nothing else fits the range. It's possible. Do the math. You can use a calculator when you take your test. Do it on paper. Use a slide rule for Mark and Mike, baby. I have slide rule somewhere. And you're free to do that. What's the resistance to circuit drawing 4 amps from a 12 volt source? Well, resistance again is E over I. So it's 12 over 4. It's going to be 3 ohms. Trying to get this thing to slide down. What's the current in a circuit with applied voltage of 120 volts and resistance of 80 ohms? Well, we want to know current, so we go to current E over R, and we have 120 over 80, so it's a 1.5 amperes. And this applies to things like in your home. You can understand how much current's flowing through wires and why you have to use bigger wire. Bigger wire can handle more current. What is the current through a 100 ohm resistor connected across 120 volts? And going back here, they want the current, so we're going to do E over I. We have 200 volts, that's E, over 100 ohm, it's going to be 2 amperes. Current 24 ohm resistor connected to a 240 volt. We want to have 240 over 24 for the, they want current. What's the current? So E over R. So 240 over 24, it's 10 amperes. it's beginning to sound like it's simpler. When you read these, they sound complicated. Voltage, a 2 ohm resistor, a current of 0.5 ampere through it. We have a 2 ohm resistor, and we want to know current. We have, so it's 2 over 0.5. It's going to be 2 ohm resistor current. So I'm sorry, so 1 volt. Voltage across 10 ohm resistor, current of 1 amp. 10 ohm resistor, voltage I times R. It will be 10 volts. What's the next? These go on. These are kind of repetitive at this point, I hope for you, because you're seeing how simple these are. 10, that's the one we did. What type of circuit? A DC circuit through all the same components. Remember we said the truck on a 1-lane road, that's going the same current going through all one, and that's in series. Connect one to another. What type of current? Is the voltage the same across all components? And this is parallel, where we have two things, put voltage on them, they get the same voltage. It's not going through them in one after another in series. It's parallel. Ooh, are we through that? We're through. Do you have questions? I didn't realize how quickly we got through all that. Can people unmute? There've got to be some questions.
Whitey's good. I'm an old double E.
Well, you don't, yeah, you don't count. For you.
That's right.
Hold on. You get to do a documentary on Tesla. Not the cars, the field. So, and you can explain magnetic dip for a compass and all that. It gets really interesting. Anybody else, any questions at all? I'd really like you to ask the questions rather than suffer through anything. And I hope we all got the little things I had passed out. This session is a really simple session because so much there's the math. It's just understanding Ohm's law, the power law, and of course, power circle, the one that's a little more comprehensive. There's this circle that I shared. We use the individual circles. This is the same thing, but I'm not going to remember this to write it down and make a drawing, but it incorporates power, ohms, volts, and amps. It's a combination of the power and Ohm's law. And if you wanted power equals these things, you can figure out what you need from that. The other one, did I not share? I don't think I shared. Oh, the formula crib sheet. This one, Bill may have shared this to you before. I think Bill shared this in a previous one. This is powerful. Basically, you're using a couple of these. All of this, whoever electrical engineer, yeah, this is all textbook stuff. This is where they get confused if you read too much of this. Right now, I gave you these little pieces, and these are simple to use. But this is nice to keep because you're going to eventually need to have this type document. I'm going to stop sharing. Any more questions?
Yes, Dan.
Yeah.
Could you explain why RF has resistance?
So when we have RF, it's radio frequency, and we have that sine wave. Normally, it's normally a sine wave. It is alternating. So there is resistance. We're sending signal down the antenna. There's a resistance to it. And it has resistance just like an alternating current. Anything you're doing with it, it's having to do getting it down the wire. There are currents involved in the antenna as well as voltages. They both exist. In fact, a lot of what we do is adjust our antennas so if things balance. It has to do with the length and things reflected. But an antenna, there are voltages and currents, and you can get areas of high voltage on an antenna, literally a spot where if you touch it, you can have high voltage, kind of like waves going by. There's nodes where you're neutral and where you're not. So radio frequency has a resistance especially going through an antenna. We don't think of it that way once it's in the air traveling through space. But indeed,
That's the question. When it's going through the air, does it have resistance?
No, because there's nothing to resist.
Okay,
Well,
got it.
Air and water, yeah, there's something, but the way we normally think of it, we don't have resistance as it's traveling through the ether.
Uh-huh,
If I can go back to 1800,
okay.
and with distance, the signal decreases, but it's just like if I shout in your ear, all the sound goes in your ear. When I go further away, it's spreading out, and the further I go, it spreads out more. That's why we can look at stars, not at our star. We'll blind ourselves. We can look at stars far away because it's spreading wider and wider, and it's weaker and weaker signal. So there is signal loss because of distance, and other things can attenuate radios, but a lot of it, think of it as blocking it, like tree leaves will attenuate, by the way, means to diminish, weaken. All attenuate means. You'll hear people use the term. Anything more? There's got to be some questions.
So Dan, Mark G, the other Mark, we've got two Marks, had put a question in chat where he thought inductance was measured in ohms. And I clarified that, but what I don't know is that maybe you had slipped at one point and said something wrong, or maybe you just didn't understand it.
Yeah, well, impedance is measured in ohms. Inductance is Henrys. Inductance, the unit used is a Henry. Capacitance is farad. Impedance is in ohms. I certainly could have misstated it.
Dan, so I also have the question about, can you differentiate a little bit more about inductance and capacitance?
Sure.
I know it's the same phenomenon, but which is which?
Just saying, let me share my screen here, just so it's in front of me. Capacitance is storing energy as an electric field, and I mentioned a classic capacitor is you literally can store it between a static field. A static charge in something is a capacitance. An inductance is storing it as a magnetic field. And literally, if you opened devices here, an inductor looks like just a coil of wire. And inside that coil, we could if we make a permanent magnet by wrapping a coil around like a nail, well, we have that magnetic field, and that we're storing energy, because initially when the power goes into the coils, it creates a magnetic field. It sits there until you release the current. Then the magnetic field collapses and can go back as current. That's really how a transformer works, is through inductive. And that's why we have these inductive cooktops now. And capacitance is a static charge. And the dangers are capacitors can be used. Anybody who's old, like me, we used to take the tubes out of the TV. You can get a static charge on the TV tubes that we used to use. The capacitors store energy in electrical devices. They can even it out. Capacitors store the field, and you can turn it off and let it come back up. Capacitors can be used if we have AC current and we convert it to DC. We can just lop off, because it goes from, here's my neutral, we go up, and then we go below it now, or the other direction, now up. We could simply draw a line and have hump, all one direction, so current flows one way. That's the cheap way to make DC current. It's not like a battery where it's just steady. And one thing you want to do is to smooth that out. There's devices you can build. It's simple wiring with diodes, which act like check valves. You build a device so they all appear the same way, but you'd have a bunch of power than nothing, than a bunch. And by using capacitors in inductors, you can have those voids fill out till finally the current looks level and steady, like you get from a battery. So capacitors and inductors store energy two different ways, electrically or magnetically. But that's used, you can use that to smooth everything out. So it now comes out steady state. A dam does that. When the river flows go up and down, and you have water flowing through a hole in a dam, the water can come steady, the river can go irregularly. The dam stores the power and then lets it go through at a later time. Capacitors, inductors are used in that manner. So inductors, magnetic field, capacitors, electrical field. Does that help?
It does. Thank you.
I'm going to go ahead and end the recording of this, and so we can talk a little more freely if we want to.
Yeah.